Welcome to another podcast. In this episode, we're going to be taking a look at trigonometric integrals once again, although this time we are going to be in the hard case. And what makes this the hard case is the fact that the powers themselves are even. So the reason that this is the hard case is because the powers here are both even, not odd. There's not a single odd power. If there had been an odd power, then we could use the trick that we used in the previous video of using the Pythagorean identity to reduce the power by 2. And if the power is odd, eventually reducing the power by 2 will get it down to a single power. And then once we had a single power, we could do a U substitution. But that's not the case here. So the question is, what can I apply? And the answer to that is a half angle identity. So let me just quickly remind you here what the half angle identity is. The half angle identity says if you have cosine squared of x, which we do in this problem, then you can replace it with 1 plus the cosine of 2x divided by 2. And similarly, if you have sine squared of x, you can replace that with 1 minus the cosine of 2x over 2. And so these two identities, called the half angle identities, are what we're going to use to do this harder case. So let's go ahead and make the substitution for both of those. So we have a sine squared and a cosine squared in this problem. I'm going to go ahead and substitute both half angle identities in. So we have the integral of this first one is 1 minus cosine, and then the second one is going to be 1 plus cosine. All right, we're going to clean this up a little bit. We've got factors of 2 on the bottom. I'm going to bring both of them outside the integral as a 1/4. And then what you notice is the numerators in both cases are a difference of squares. And so if I combine them or FOIL them, I'm going to get 1 minus cosine squared of 2x. So I'm going to repeat this process again because we wound up with another cosine, although this time we have to be very careful. We have 1/4, the integral of 1 minus. Now here's what we're going to replace the cosine squared with. Cosine squared of 2x. Let me just do this off to the side, and I'll highlight the differences here. Cosine squared of whatever is going to be 1 plus cosine of 2 times whatever divided by 2. And in this case, we're looking not at cosine squared of x, but we're looking at cosine squared of 2x, which means the formula is going to be 2 times 2x, or 1 plus the cosine of 4x. And so that's an important distinction here, is that because we've applied it multiple times, we're going to have a larger final frequency than what we started with. Alright, so if I work on this a little bit more, let's see, we've got 1/4 here, and we're starting to look at the integrals here. So we've got the integral of, this is 1 minus 1/2 minus cosine of 4x over 2. And one more here. 1/4, 1 minus 1/2 is 1/2, minus, let's see, cosine of 4x over 2. Both terms share a factor of 2, so I'm going to go ahead and bring that out. So it's now 1/8. 1 minus the cosine of 4x. Now, at this point, we can actually do the integration step. So I'll finish that up here. We've got 1/8. If I take the integral of 1 with respect to x, that's just x. And then if I take the integral of cosine of 4x with respect to x, the integral of minus cosine is minus sine. Of 4x, And then the question is, what do we do with the 4? Well, remember, if you were taking the derivative, you would multiply by 4. So instead of multiplying by 4, we are going to divide by 4. And so the last step is to distribute the 1/8. And so we are done. So all in all, not a bad problem. It's just the harder case because if you have powers larger than 2, you're going to have to do this over and over and over again. If you had an integral of sine to the 6th power, for example, you'd have to use the half angle identity 3 times to get it down to a place where you could actually work it by hand. Now don't worry, I'm not going to give you one of those. That's too tedious to try to do by hand, but I at least wanted to expose you to the idea of reducing powers of the trig functions using these trig identities. And that's the sort of the important observation here with these trigonometric integrals. All right, thank you for watching.